we want to avoid race condition. We avoid race condition by having multiple elements, and each element is going to be used by individual threads. Okay? So when they share this partial sum, they potentially cause race condition, but individual thread is going to be assigned to each one of these elements, and they will touch on it. So they are not going to have race condition in this case, even though this is shared. But having them too close to one another, we got force sharing. So we have to move them apart in order to increase our performance. Now we have to make a lot of consideration. Because of that, OMP actually have a keyword here. That keyword is for reduction. With this for reduction, then we don't have to worry much about doing this partial sum. We let the OMP do it for us. So that's one thing. Second thing is, when we write the code just like the single thread. We don't have to worry about starting the ID, and then you have to increment by total thread. We don't have to do that. We can start on 0 and then increment by 1. Why? Because the OMP will handle it for us. So whenever you increment for you 16 times, or whatever number of threads that you created. Okay? So the keyword to use here is for reduction. By using this for reduction, now you don't have to do all the hard work. The OMP will do it for you. And this only applies to OMP. OMP has this feature. MPI don't have this, GPU don't have this. So you have to learn back what we are learning, part A. Because part A is important for you to solve MPI problem, the problem in the MPI platform, and also GPU. Because GPU and MPI do not have this feature. Only OMP has this feature. Okay, this feature is useful because without this feature, you have to do it yourself. With this feature, then you let OMP do it for you. Okay? Take note, GPU and MPI don't have this feature, so we have to solve this similar method like this in MPI and also in GPU. But GPU and MPI don't have force sharing, so that is one advantage. But what you have learned in A needs to be applied in MPI and GPU, so you have to remember that. But part C, we avoid all this. So how do you do this part C? Very easy. You go to your first program, which is your original program, and then you apply this part paragraph for reduction on the code that you need to run in parallel. Okay? So you don't use the modified code, you use the original code. Okay? The original code, and then you apply this in the code section that you need to run in parallel. Okay? Now, how do you use this for reduction? Let me show it here. The proper way of using it. Because if you use it in a wrong way, you generate error. To avoid error, you need to understand how you should use that. Okay? First thing is, let me show you the Pragma OMP alone, OMP parallel. Now you open the brace here, and then you can have multiple statements, and then you close the brace, right? Because this OMP parallel can take in multiple statements, and if you want this multiple statement to run in parallel, you have to enclose within these braces here, right? That means this Pragma OMP parallel can actually handle multiple statements. But if you have 4 here, this 4 keyword, then it will be slightly different. Okay? I just put 4 there without the reduction, because without the reduction you can have 4. Okay? You can have 4 reduction or without the reduction. It's the same thing. Now for this, you need to make sure that the next instruction is a for. Here, the first instruction do not need to be for. If you look at your code, it can be integer something, it can be any kind of arbitrary equation, right? But for this, because of this for, you need to be, the next statement must be a for loop. Okay, it must be this for loop. And then you can have multiple statements. That multiple statement must be inside the for loop. Okay? And this part mark 1 before, it cannot have like this. You cannot have another statement there. That means you cannot have for loop plus any other statement. Okay, because it only handles the for statement. It doesn't handle any other statement. Only one statement. For statement. So you don't put this. You don't put the open brace here, close brace, and then some other instruction inside there. Because it will not handle, it will not run all in parallel. It will run in parallel for this for loop only. Okay? And it must be for because of this for. Okay? Whether it's for reduction like this, is the same thing. Okay? So that is the rule for this for keyword inside this part. Oh, sorry, I missed something there. Parallel. Okay? Part 1 to parallel for. Okay? Now there's another thing that I need to tell you is this. This for loop, you can actually create I and J, K or whatever variable inside there, right? You can use multiple variable inside this single for loop. But if you use only parallel for, you can have only one variable inside. You can name any name, but you can have only one. Okay, you cannot have I, J inside the same for loop. Okay? And this I here automatically become private. So you don't have to make it private. Okay? Even though you don't make it private, the for here will make it private for you. Okay? And there's only one variable. You can name anything, but only one. Okay. Now another thing is, because this is going to run in parallel, that means multiple thread is going to run it. Okay? If you declare inside here, you're going to be private. If you declare a variable outside, it's going to be shared. And you have to be careful with the shared. Okay? Because if you don't be careful with the shared, you have race condition inside there. Okay? So even though it helps, if you use for reduction, it helps a lot. That means your code is going to be, it looks like it's going to be like original code. But you have to worry about your shared and private variable. If there's the variable needs to be private, you have to make it private. Okay? Put private here, or you declare it as a private variable. Okay? If you don't do that, you won't get an answer. Okay? So you must make sure that private variable needs to be private. Shared variable, you can leave it as it is. Except for the I or J or whatever thing that you use here. Here you don't have to put it as private, even though it needs to be private, but because this for is going to handle it for you. Even though you don't make it private, you will force it to be private, right? So that is the thing that I need to tell you. So right now what you need to do is, you go to your original code, you make a copy, look for the for loop, the one that you need to run in parallel, and then apply this on it, okay? Now what does it mean here? Reduction plus colon sum. Okay, let's have a look. This problem here. Remember I mentioned to you that we solved the problem we had. We got a variable that needs to be shared. Now if we share the sum, you're going to have race condition. In order to avoid it, we create an array of variables. Okay, array of sum. Okay, and then we assign the thread ID. The thread ID 0 is going to use element 0 of this array. Thread ID 1 is going to use this partial sum. The shared product sum. Okay? So thread ID is assigned to individual of these elements here. And they're going to only partial sum their own one. They're not going to touch any others. That's why there's no race condition. But eventually, the result is going to be reduced. It's going to be reduced to sum, right? And who is going to do that? Thread ID 0 is going to sum them up together. That means you are reducing the result into 1, right? And this action of doing this is reduction. Okay? And when you reduce it, what do? You add 9. You add them up. Okay, you add them up. That's why when you reduce by adding. That's why you see a plus there. Now, if you reduce by multiplying all of them, then here must be multiplied. Okay, if you reduce this by subtracting them, then you need to subtract them. Okay, or if you reduce by dividing them, so you have to divide them, right? So divide means you have to put backslash. Sorry, slash, forward slash. That is divide. So this plus, this symbol here is actually the action that you do. What do you do when you reduce? Okay? So basically, reduction is you're asking the OMP to make that sum as shared so that it can be accessed by all of the threads. Okay? Just like what we did here. But then, because it is shared and you have race condition, so you're asking the OMP to make it into array, okay, and then sum them individually by the threads, and then eventually reduce it to the sum. So basically, this reduction here is asking the OMP to do the same action that we did just now, okay, in part A, except that we don't do it. We let the OMP do it, okay. And we don't have to worry about thread ID. We don't have to worry about total threads because everything is done by this core reduction. Okay? So I want you to try this. This one actually is very simple. Just use the original code, apply this there, and then whatever inside this for loop there, whatever inside the for loop, it needs to be private. Make sure that you declare it as, define it as private. Okay? If you don't do that, then your answer will be wrong. You won't get this answer. Okay, I'll show you how it looks like. I think I showed you already, right? No, I haven't showed you yet. So, I already solved the problem. I call it multi using reduction, and this is the result. Okay? So, this is the original one. This is with 4 sharing. This is without 4 sharing. This is with the reduction. Okay? So the result is more or less the same, it's comparable. Here it looks like it's slower, but if you look, it's actually more or less the same performance gain as what we have done before. If you run the second time, maybe it will be faster. But they are comparable. Okay? That's quite good. Okay, it's, now it's faster. Slightly faster, but actually it's comparable. Why? Because OMP also do the same thing like what we did. Except now the program is much simpler. Okay, you do this, get the result, get this result, and then you compare what you have done and what you write in this for reduction. Okay, you see that the code is much easier. Okay, it's only OMP providing you this. Unfortunately, FPI don't have this feature, GPU don't have this feature. So you have to suffer again when you learn GPU and FPI. Okay, if you are doing for OMP, then you are lucky because it has this 4 reduction provided. Okay, try it and then let me know if you get any. Okay, what did I do there? Actually, I returned the time. Okay, let me show you how I return the time so that I can compute this. Okay, let's have a look. So single, initially I returned void, but right now I return double. And what I return the time. Okay, the time difference, the period taken to solve the problem. And I do it for all. I do it for single, for multi, and for reduction. All of them will return their own time. And when you return, it returns to this variable, or this variable that you see there. Okay, I collect them, and then I compare with the original. Okay, so I compare with the original. And that is why you see this performance here. So this one tells you that it is 3.6 times faster than the single thread. This one is 15.5 times faster than the original single thread. This is also the same thing. This is 4 reduction result. It is 15.7 times faster than the original result. And from here, because I got 16 threads, so this number here will not be bigger than 16, right? And of course, I know that if I increase to 32, I'll still see about 15.7. That's to show to you that the number of cores that I have in this processor is only 16 cores. Okay. Now, if you go to GPU is different. GPU we have 2,000 cores, 2,000 plus cores. But if you use CUDA only use 1,000 cores. So we have 1,000 times faster maximum. Okay. And of course, our CPU cannot beat it. And that's the reason why you see a lot of people use GPU rather than CPU when we have higher computing processors to run. Okay? Especially big data and AI. Okay, AI use, that's why, because of AI, that's why GPU is very expensive now. Okay, because there's only one vendor that is selling it, which is NVIDIA. I think the popular one, of course, AMD also produce their own GPU, but their GPU is not as good as NVIDIA. China is coming out with their own GPU as well, because of the sanction. Maybe in the future we'll find more GPU, but at the moment, we study NVIDIA first, because NVIDIA is the most popular one. Okay? And it's good that you know this, because in the future when you work, most probably you might end up in a company dealing with AI, right? Because every company that approaches, they want to collaborate with us, the first thing in their mind is AI. Okay? So you will face AI most of the time when you go to work. Now, when you do AI, definitely you have to know how to use parallel computing. Because if you do not know how to use parallel computing, then you cannot train your AI. Okay? Or maybe if you want to run your AI faster, you have to use GPU. Okay, try this and let me know if you get a result or you don't get a result. Okay, you should get close to this number. 15 times, 14 times is close to this number as well. Please make sure the answer is correct first. Don't look at the performance here first, look at the answer first. The answer needs to be accurate to 9 or 10 decimal points. In my case, it's 10 decimal points. You can see all of them. The first 10 decimal points are the same. Okay, all of them. The rest, they are not the same. It might be different because of the accuracy. You increase the number of steps, the more accurate it is. Okay, so we already analyzed this in our first practical. For 100 million steps, it is accurate up to 10 decimal points only. That's why I only highlight the first 10 decimal points. Okay, if you compare all of them, the first 10 decimal points are all the same. That means this solution is correct. Then only you look at the time. Okay? Now only this time is meaningful. Otherwise, it's not meaningful at all.
Teacher, can see your find pi multi-tool.
Huh?
Can see the function, the find pi multi-tool.
Which one?
I want to see the function multi-tool.
You want to see what you return? You return double.
No, I just want to see the function. How you write it?
No, you cannot see the function. You have to do it yourself. That's why I asked you to do it yourself. I can give you the answer, but it's pointless, right? Once you see the answer, you're not going to learn anything. What I want you to do is to try yourself. Okay? That's the reason.